Hello and welcome to day 14 of the Advent of Code Stream 2020. Happy Monday to y'all, and I guess the thing to talk about here is that I did finally get day 13 part 2 to work after we ended the stream last night. So I'll talk a little bit about what I did there while I kind of get set up for day 14. The key realization was that basically, if you remember, we talked a little bit about how the numbers all kind of line up, right? And if we take, and by line up, I mean they all start together, and because they're primes, their product, aka their least common multiple, will sync up, so to speak. It'll line up again when you multiply them all together, right? That's the upper bound, so to speak, for when they will all come back together. It's not the right answer, but everything kind of cycles around. Think of it like a clock, right? The seconds, the minutes, and the hours hands all start at the same moment at midnight. And in the case of a clock, because they're multiples of each other, everything comes back together every hour, not every 24 hours. So, every 12 hours, right? Because it's the hours are 12, the minutes are 60, the seconds are 60. So the least common multiple of all of those numbers is still 60. That's why they all line up at midnight, at the top of the hour. So the point here, though, is that the same thing happens for these offsets. Like, two prime numbers don't become one number apart or three numbers apart or however many numbers apart more than once because they're not multiples of each other. So in order to cycle from kind of them all being lined up at the start of the buses till when they kind of get lined up again down the road at their product. So let's say it's like 13 and 17, right? So like from 0 to whatever 13 times 17 is, between those two numbers, every kind of position is unique. Every paired position is unique in terms of their relative offsets. And so what I ended up doing was, and this was kind of a combination of that particular realization that they are all, they only cycle through once, and looking at this, realizing that these are, a unique set. So when we're at 13 and 19, right? Let's say the offset we're looking for is when 13 and 19. So we're just going to look at those two, not like a whole bunch. Let's say 13 and 19 need to be like 2 apart. So they're 2 apart at when 13, the first bus, is at 169. And so now we know that every cycle through, every 13 times 19, what is that? 247. Every 247 numbers, right? So it's like if you imagine a loop where you are jumping 247 at a time. Within each of those 247 number blocks, at 169, inside of there, is where these two numbers line up. And so you can have 247 and then another 247 and another 247, and inside each of those kind of passes where the clock comes around, right, and they all line up again, during that pass, the moment when they are exactly this offset is right here at 169. And so when we then extend this idea to another number, let's say we added a third number here, one of the numbers I had, I think, was 59, right? So to find that maximum kind of resync offset at the far end of the not distribution, but like of all the cycles, and they all come back together again, it's 13 times 19 times 59. So that means we're going to have 59 times 247, right? 13 times 19 was 247. So we're going to go through this 247 block 59 times. And inside each of those, we know precisely where 13 and 19 are going to be 1 apart. It's going to be at that 169 within each of those offsets, okay? And that's the only one that it can be. Like within each 247, it doesn't matter if the 59, right, our hypothetical 59 here, is like lined up correctly. It doesn't matter because 13 and 19 have to line up too. And so we can basically say that within each of these 247 blocks, we can jump every 247 and only check at position 169 to see if the offset for the divisible by 59 is correct, right? So we saw like things like this where we had t plus 4 divisible by 59 true or false. And so we would check each of those 59 positions. There's only 59 things to check at the offset of kind of range offset 247, but the whole thing shifted by 169. And so once you find that one, now you know where 13, 19, and 59 are lined up, right? And so then you can go on to checking 31 in this case, right? And so what I was doing was I actually wrote this in a Scratch file. So what I originally had was I checked 13 and 17, 7 and 13. And I just had a simple loop there. I just counted every number. So this is the final form. But then what I did was I said range and then 0 to, let's say, at the beginning it was 7 times 13, right? And I said, I just counted every one. And then I said, if they're both divisible, right, with their appropriate offsets, I literally copied these little equality statements straight from my notes here. It was really perfect. And then we would print the value. And in this case, it was 77. So 77 is divisible by 7, and 77 plus 1, aka 78, is divisible by 13. And so now I knew that the offset was 77. So what I did was every time I comes around, whatever the I looping was, right, we start at 0, then we add, in this case, 7 times 13 per time. So I changed the range to have 7 times 13, and I upped the upper bound of the range to be 7 times 13 times 59. But then what I did was I said t equals I plus, at least in that first iteration, 77. So I was adding the kind of matched location that was found to the base index, the ith value. And because it changed each time, I didn't want to change where the range started. What I wanted to do was add it to the base value because it still needs to start together. And so then I added this print statement, and I added some tabs in front of the print so that I could see it. And the way this printed out is actually fascinating. So when I run this, you'll see here, it prints it multiple times because it matches this too. By definition, we've constructed it that way. And so if I take away some of these, right? Oh, it's because of the jumping, right? So, so then what happens is, you find out, you learn that every 7 times 13 times 59 cycles, values, the right matching number is 350. 350 is the one that is divisible by all of these numbers. And so at that point, I had kind of this indented thing that said 350, 350, 350. And then I took this, I increased our ranges yet again. I added 31 to the top of the range, and I added 59 to our step counter. So now the range is moving every 7 times 13 times 59 steps at a time. And so this allowed our algorithm to run over an iteration count of 7 plus 13 plus 59 plus 31. Rather than having gajillions of numbers, I was able to check only the handful of possible values. And so that was the key realization, basically, was that the numbers sync up only once every least common multiple when they're multiplied together, but they're also offset in unique ways once per cycle. And that we could check them, and the final insight was that we could check these kind of cycles, these types of chunks, in incremental fashion, that we could do just the subproblem of 7 and 13. That's kind of what I was playing with here in the spreadsheet too, right? We were saying, what if there was just these two? How does that play out? And so, yeah, I mean, that is essentially it, right? Then we just go through, and I did this manually, and I actually went till the end because I was just like, I just want to see it all work. Coding it was a little bit more tricky. what I ended up doing was I wrote, so the function that I wrote, part 2 v2, this first part is the same as before, and I basically thought through kind of how this worked, and tried to encode it in as a kind of methodological approach. It was a little bit tricky because what I wanted to do, I couldn't find a way to like run it in one pass, like, because when I was doing this by hand, I basically, computed one thing, then found it 77. Then I had to take that 77 and put it up here. I said t equals I plus 77, and then t equals I plus 350. And I was changing the range each time. So I decided to just go with it and do exactly that, right? Rerun the for loop each time as I'm kind of iteratively finding those intermediate values. And so we can see here that this function check match does exactly that. It runs the range. It has this what I call the range top and the range step, right? That's the top of the range and the step value. And so this function will expect proper values to be passed in here. And there's also a search offset, a third argument, which is what we do to I. We say t equals I plus search offset. So that's basically the return from the previous call. And I'm also realizing that this variable doesn't get used, so ignore that. And what I realized when I was running this is because we're running these offsets, and because when I was doing this, remember I said that I had this like triple printing problem where I printed multiple times, and then one of these is correct, and it's this one. It's the one that prints one more than all the others. It's checking every single one, and then at some point, there's one more. And so that's the one that lines up with like whatever the final thing is. And so here, I don't need to check all the ones before it. I know they'll work, right? You see how like it just prints it prints every single one 3 times, and it's just useless. And so what I realized I could do is just get the last thing out of the schedule that is being passed in. So the schedule only goes up to whatever up to whichever one I'm checking. And so I take the last one, and that's the only one I need to check. If that one matches, that's all I care about, because we're only checking the kind of ones that are already known to be proper multiples of the previous divisors, so to speak. That's what this range step and range top is doing for us. We are skipping, every 77 or every 350 values, or not, every, not 350, but 7 times 13 plus 77, or 7 times 13 plus 59 plus 350 times 59 plus 350. Yeah. And so then then it was this function itself, right? How do I call check match? I call it in a loop where I'm going through my bus schedule. I decided to have the bus schedule be the bus ID offset in pairs, and so as a list. And so I was able to get the ith value and the 2 offsets. And so what I was doing was I said range top is just the product of the bus ID that's coming in, and we're just kind of accumulating that. And range step is kind of lags one behind, and so I'll do that after I call check match. So that's why this is down here. It's basically the next cycle. It's waiting for the next cycle to come through. Now check match itself, right? It does all of this stuff, and you'll notice I'm passing in a schedule from the beginning until I plus 1. And so that kind of limits the top end of what of the list that schedule is passing in. So it's slicing that schedule to just be up to what we care about. So at first it's like 7, and then 7 times 13, and then 7, 13, and 59, and so on. And so check match returns a number. Sometimes it doesn't return the right, like it goes through, right? It doesn't find it or something, so it can return false. But usually it returns a number. And so I'm kind of taking a little bit of advantage of the integer truthiness. And so I say if it's found, then the search offset is found. The first time through with the 7, the initial conditions I didn't quite get right. And so I saw there was a bit of a bug there, but this kind of gets around it. And then it finds it, and we can print it. So I'll show you what it looks like here in our small input, just to demonstrate the use case here. So here's our input. And so you can see that when we run this, I have some print things, right? So the first one, it finds a 0, and that's what I mean by it's like a little bit strange, but then it finds 77 properly with these 2. And then it goes and it says, you know, every 91, which is 7 times 13, offset 77 on this schedule. And so you see the schedule is extending longer and longer each time. And we just find each one just like clockwork, you know. And what's interesting here also is that if we were to print I'll print T outside of this if statement, just to show you, like, it's really not doing that many checks. So T, print T, and we can say like checking something like that. And so you can see it runs so fast. And so you can see here it's checking 1, 2, 3, 4, 5, 6, and then it's checking multiples of 7, right? And then it's going to check, and it gets to 77. Now it's going to check every 91 offset by 77. So it's like 168, 32, you know, it's jumping like that. And now it's going to check every 5,369, right? That's 7 times 13 times 59 times 31. No, just times to 59. So it's everything but the last one. And so and then it's checking every 5,000 values offset by 350. And then it's checking every 160,000. So it's like really improves our efficiency a ton. And that's for the example one, the one that we were able to run without needing any sort of you know, special stuff. We were able to brute force that one, no problem. But when we run the full thing, we see it still runs super fast, but it's a little bit bigger, right? So it's checking every 1,000, and eventually it may or may not find it. You know, this one, you know, it looks for a while, but it gets there. And then, you know, this one was a quick find. It got lucky. These two numbers lined up pretty fast. And this, you know, but like, look at these numbers. It's checking every 11 million numbers, offset by 1.5 million. So like, if we were checking these in any sort of like constant time skipping, like I'm going to check every 7 values, or I'm going to check every 7 times 13 values, it would be crazy. And this is kind of where I think I figured out the intuition for this, is that like I was thinking like, well, I only need to check every 7, but then I was like, oh, but then later I only need to check every 7 times 13. And then later I only need to check every 7 times 13 times 59. And so you could see how the increase in number of multiples makes the spacing larger and larger that we have to check. And so you see towards the end here, we're jumping huge chasms, right? Like this is what, 2.5 billion offset, and then we have a, what is this, 1, 2, 3, 4, 5, 6, 48 billion offset. Like that's the range kind of step size with a 26 billion 26 million billion offset. Was that 48 trillion? No, 48 billion. I don't know what these numbers are. Yeah, billion. And we're still going, and eventually it still has another round to go. Not quite at the end, out of the woods yet, but like, look at how big these numbers are. I'm so glad Python is able to handle this. I know there have been times where it's like, Python might not be able to handle this, you know, but this is 21 trillion. And so then we find our number at the end. And so what a journey. Didn't really end up using that much anything special from a modulo, or like there was no fancy modular arithmetic here. You know, I just had this one thing. Does it divide? That's it. You know, and everything else it ended up just being good old logic, good old fashioned logic. So I hope you found that interesting. Now let's move on to day 14. I'm going to open up our inputs here. I'm going to run our, come on, what happened to day 14? It disappeared. I'm going to undo some of those changes we made in day 13, take away that print statement. Good. And so hopefully day 14 doesn't use that insane stuff that I just did from day 13. This reuse stuff, really trying to shy away from it this year so far. Let's hope that sticks around. So with that, let's start the stopwatch on day 14 underway. Here we go. As we approach the seaport, the captain asks for your help with the computer system that runs the port isn't another port compatibility problem. So the docking parameters aren't being correctly initialized in the docking program's memory. All right. I think I can work with that. Let me adjust the sound briefly here. Okay, so we discover that the Seaport's computer system uses a bit mask. Oh no, its initialization system. You don't have the correct decoder chip. You can emulate it in software. The initialization program either updates the bit masks or writes a value to memory. Values and memory addresses are both 36-bit unsigned integers. Oh, how nice of them to use 36-bit unsigned integers. Ugh. Ignoring bit masks for a moment, a line like mem8 equals 11 would write the value 8 to memory address, 11 to 8. Oh man. The bit mask is given as a string of 36 bits written with the most significant bit representing 2 to the 35 on the left. Oh, not base 36. 36 bits. Okay. And the least significant bit 2 to 0, the ones bit on the right. The current bit mask is applied to values immediately before they are written to memory. A 0 or 1 overwrites the corresponding bit in the value. I just don't really remember what this is referring to, while X leaves the bit in the value unchanged. A 0 or 1 overwrites the corresponding. So it's not like a mask where it's like doing truth false, or anding stuff. It's literally just like changing the value. So this program, by specifying a bit mask, the mask it specifies will overwrite 2 bits in every written value. The 2's bit is overwritten with a 0, and the 64's bit is overwritten with a 1. The program that attempts to write 11 to 8, we expand everything to bits. The mask is applied as follows. Yes, so this is decimal 11, decimal 13, or 73. Converts this to a 0. Interesting. How should we go about this? So then the program writes 101 to memory address 7. Oh, that's the next thing, right? Yeah, it writes 73, that's this. Then it writes 101, which is this whole thing. Keeps the 0 the same, keeps the 1 the same, writes the 0, which will write 64. To initialize, we need the sum of all values left in memory after initialization completes. Okay, the entire 36-bit address space begins initialized to the value 0 at every address. In the example above, only 2 values in memory are not 0. 101 and 8 are address 7, address 8. Oh, we overwrote the old one. Okay, I see here. All right. It's doable. Let's see. Oh, wow. That is not what I expected at all. There are different masks. Come on. What? All right. That was not very nice. There are different masks. Okay. So we say sometimes there's 5, sometimes there's 5. Is there always 5? No, sometimes there's more than 5. So we're going to read through each one. We could at least split on the equals with trimmings. Space equals space. We could do that. I want to keep the mem stuff because of... Oh, man. Excuse me. All right. Let's get this little example in here. Let's split line dot split on space equals space address number, something like that. They'll still be strings for now, and we'll base on what the first part is, right? Okay. So we can return that, and we're gonna get a list of lines for, and this is still plaguing us. All right, for address number in lines, we're gonna convert and detect the next block. So our like current mask, and I still need to think about how I want to manipulate these, because it's like straight overriding is not a and. It's not an or. It's not a sum. It's not a product. It makes me want to say I should makes me want to say I should do a separate mask, two separate masks for the zeros and the ones. So like, let's press enter for a while and skip past yesterday's panes and go to today's panes. All right, so if we have a mask that is, we'll take our example here. And so we could say that this should be equivalent to kind of applying two separate masks. One that is all zeros except for where the one is. And then the other one that is all ones, which will run an or statement or an and statement. Yeah, we'll run an and. So this one will say or. And this one we'll do as an and. So we can take the number and we can and it with this, with the full complement, except for this one tweak here. You still see that? Cool. And we can and it with this. So the value was this whole thing. And we want to change. We want the one to change it. So where they give the one, it's a or. So this one here, ors with the value, and it turns it into a one. Whereas, not this one, but the actual number. And then whereas the and, we and it with the value, and so most of the values are 0, and then wherever there's a 1 that we need to change, we can change it by doing that. I think that works. Let's find the positions of all the ones, find the positions of all the zeros, modify our bit strings, our kind of or and base strings, and then convert them to a number, and then we can or them together. Something like that. So like this is, or that one is 64 as a decimal. So if we did 64 and or I'm trying to remember the, okay, yeah, the Python bit operators are just the kind of C booleans, but with just one instance of the symbol. So and or are the bar, or the ampersand and the bar. So this or in this example is 64. So we did 64 or 0. 64 or 0 is still 64. And I want to try another one. And I'm assuming the order doesn't matter, but right? Yeah, because that would be insane. And then this is 11, and our mask, the mask that matters is So what is the OR mask? So this is 11 or 64. Yep, 75, but with the 2's position turned to 0, it reduces it to 73. So the bitwise manipulation is working there. I want to know how to convert this to, I want to AND it with 11. So this is 11 and int this whole thing 2. I guess it really should be 75. Whoops. Hey, great. And just for curiosity, I mean, it is a number, you know. So can we do 11 or 64 and that? 11 or 64 and that. And order of operations is intact here. Even if I do that, it's okay. So it doesn't particularly matter. Great, great. Okay, that is promising. So let's get our base ands and ors. Well, I think we just construct it, right? Like, current mask equals quote, quote. And, you know, each time we get when this first thing is a mask. So if add equals mask, then we're going to go through each thing and, oh wow, these are sufficiently complicated. So if it's a 1, we're going to append a 1 to our AND string. If it's a or string, and then if it's a 1, we append it to our AND string. And if it's X, we append the normal kind of numbers, whatever it would be otherwise. Something like that. Yeah, this is, I know it's a bit of a lazy way to do it. And string, and then have an or string. We just have to make sure we're appending stuff to everything every time. So then we say, let's see. Actually, let's make a little function for this. Let's say get and or, and we're going to pass in the num. Let's see, it's split. So yeah, that's the whole thing. And we're going to grab the 2 masks out of it. So we can say and string or string. Come on. I wanted to keep that name. Or string. And actually, I'm going to reverse this just because it's reversed in my text document, and I feel like I could potentially mess that up. Def this. I know you all hear the banging from upstairs. Somebody's doing construction, you know. This is New York. All right, for value in num, if value is X, then, oh yeah, we need to have our AND string, our OR string. Wow, that is really loud. If it's an X, then OR string plus equals 0. OR string, yep. And by 0, I mean 0. And string plus equal 1. If the value is a 1, then we're going to have a 1 appended to the OR string. OR string gets a 1. And the AND string also gets a 1. Oh, I see. So if it's a 1 or a 0, we just append whatever the value is to each of them. All right. That's an interesting way. Yeah, that when there's nothing there, they're separate, but when there's something there, they're the same. So then we could just say instead else or string plus equals v and string plus equals v, and return or, and let's see what that looks like for our small input. Takes 0 arguments, but 1 was given. Well, and nothing comes back because nothing was printed. Great. So for some reason we printed 2 things. Oh, right, the and the or. That is what we wanted. Nice. Very nice. And can we just parse one of the big inputs? Or all of the big inputs? These are numbers. That's for sure. What do they mean? Is this remotely correct? So that's the or, so it should be all zeros on the x's. So, and ones for the and. So whenever there's an x, we have a 0 and a 1, right? And then whenever there's a 1 or a 0, we have that same value. So whenever you see here, when it's a 1, everything's a 1. When it's a 0, everything's a 0. Cool. That wasn't too bad. So we get our bit masks. So the next thing we need to do is, when it's not a mask, we need to retrieve this position, this thing, which looks like it's whatever comes after the bracket until the next bracket. So this whole thing, I know there's clever ways to do this, but what if I wasn't being clever and just did that? Right. There's no attribute split. So the first thing we do gets me everything after mem. Oh, you know what? It's always going to be those characters. It's going to be positions 0, 1, 2, 3, 4 till 2 from the end. 0, 1, 2, 3, 4 till 2 from the end. So else num at position 4 till 2 to the end. Right? That should work. Like that. And our register equals a integer version of that. And that is what we're going to write to our, what are we calling this? Program, initialization program, memory, memory addresses. Mem is this dictionary. So we say mem at this dictionary location is this number. Yes, this number. This number. Oh, it's actually add, not num. Ooh, close call. Equals this number, which is num, turned to an int, because we're still holding on to a bunch of strings, right? Or did I convert it? No, I didn't. It is still a bunch of strings. And we're going to take our mask, whatever the mask is currently, and I lost my thing in the Python console. Oh, no, I didn't. So we're going to take the number, int of the number, or it with our or string turned into a number, and it with our and string turned into a number, right? And it with our and string. Our and string is the one with a bunch of ones turned into a number. And that's our converted. Then we can do return the sum of mem.values. Something like that. Oh, I'm already running the big one? All right. Nope. All right. Got too jumpy. All right, let's see what I did. What it actually should have been. What I should have done, of course. But you know, this is Advent code. You just YOLO it. What did I do wrong? Invalid literal for base with int 10. Quote. Huh. If add equals mask, where is that happening? 0, 1, 2, wait, 3, 4. 1, 3, 4. Am I doing this wrong? I mean, it's very possible. I've been known to do things wrong many times. I did not grab the last number. And that is why my answer was wrong. 165. 165. Let's run it with the full thing. Do you think it's been a minute yet? No way of knowing. Oh, still no good. Now my answer is too high, it says. Before it was too low. Interesting. Meep. All right, so what is the dealio here? I mean, these are huge numbers, so I mean, I could print out the memory space and just like, you know, each time. But it's really big. And there's lots of memory addresses. So count equals 0. Count plus equal 1. Oh, let's move that down actually. If count equals 4, break. So we can do a couple here. And we can take a look at this input. So the first number that we see is this position. So 1, 2, 3, 4. I'm assuming we haven't processed this one yet, and that's the only reason we don't see it, is because I'm adding to the count before checking it. Great. And we are getting the right indices. It remains to be seen whether I'm getting the right numbers, though. It is interesting that we have a pass that is an empty dictionary. Because the first time through, yep, there's nothing there. We're just setting up our masks. And why not return the converted versions of these? I don't know. Yeah, because we're going to reuse them a bunch anyway. So let's rename this to be and mask, and this to be or mask. And I'm gonna take this little bit here and string. We're gonna convert this from base 2, convert that from base 2, so the OR and the AND masks get returned, and then we have our OR mask and AND mask. And I guess we could even compute their See, this is the thing that gets me, right? Is like, I could merge these. Why don't I merge these? And do I just end up with the same thing? If I say OR mask and mask, so these are all then zeros. And this is the only one. But we lose data. Well, these two, the 0, 0 here stays 0 because we're ANDing them. So it just becomes zeros, all zeros except for this one is a 1. And then if we say and that, or then we OR it with this, with the original value, which was what? With, as an example, our original value being 11 here. We OR that with this. So if they're all combined, right? So the only one that we really see then is this one, because the zeros are still zeros and everything is a 0, blah, blah, blah. And we would OR it. So that causes that 1 to be changed. And we OR it with that. This is 0 or 1. That doesn't change it. And if we're here, this is a 0, 0, 0 mask. They're saying OR, so these all pass through. Do the zeros just not matter? Well, it does, because when there's a 0, it becomes a 0. So it's not like an OR, it's like an and that's why this matters. I think it's an order of operations problem. Not really sure. Actually, let's just do that. Do we get a different input? I mean, different output here? We do. And it is smaller. That's crazy. All right. Oh my goodness. It's the order of operations problem. All right. Yeah, I guess, yeah, we do want to do it kind of like one at a time. You know. But still, did not expect that. Yeah, the and takes precedent. If I had it flipped, it would have worked. What did I have over here? I did have 11 or 64 and I tried it with different combinations and it gave the same number. So wacky, wild, and crazy. 28 minutes. Eesh. Been better. I've been better. All right. Let's see part 2 now. Still can't communicate. V code V2. It doesn't modify the values being written at all. It acts as a memory address decoder. Immediately before a value is written, each bit in the bit mask modifies the corresponding bit of the destination address. If the bit mask bit is 0, it's unchanged. If the bit mask bit is 1, it's overwritten with 1. If it's X, the memory address bit is floating. It fluctuates unpredictably and take on all possible values, causing many memory addresses to be written all at once. Very clever. Man. All right. Consider this program. 42 equals 100. When the program writes to memory address 42, it first applies the bit mask. So the X's carry through. The 1s are 1s, and the 0s do nothing. So it's an OR, strictly speaking. Yeah, this is an OR. Is it? Yeah, it's an OR, because when there's a 1, anything ORed with a 1 will always be 1. And anything ORed with a 0 will always be unchanged. Yep. It's an OR where the x's are zeros, except we need to treat the x's special. 4 bits are overwritten, 3 of which are different, 2 of which are floating. Floating bits take on every combination. 4 actual memory addresses are written. Oh boy. We're going to have a lot of combinations, but we have to write all of them, don't we? With a different... Yeah. 3 memory address possibilities. The entire 36-bit address still begins uninitialized, and you still need the sum of all values left. Okay, it doesn't say anything about it being like impossible, which is helpful. It doesn't look like there's like a insane number of x's per line here, which is also helpful. We're gonna need a different decoder function. That's what we should call it. Decoder. So much more fun than get and or. What was I thinking? I'll still use parse1. Yeah, I'm still happy with that. So I'll grab this. I'll just grab the end and then we'll make some changes. How about that? Okay. Getting there. So I can see where this is headed at least this time. So we need to... Ooh, what do we need to do here? The x's can be any possible value. So when we decode, so it's about having these values be the same and those values be different. I'm trying to think if there's a good way to calculate these values or not. There might not be. So let's take a look at this case, because what I see is mostly that 26, 27, 58, 59, right? So the ones bit is floating, as we saw, and the 1, 2, 3, 4, 5, 6, 2 to the 6, the 6 bit is floating. Actually, it's the 0th bit and the 6th. 0, 1, 2, 3, 4, 5. 2 to the 5 is 32. 26 plus 32 is 58, I hope. It is 58. So every position that has an X gets their kind of 2 to the ith position, moved up. We'll iterate from the back to the front. Here we have X's in a bunch of places. And so when we have this, each time we have something, right? Well, we can do the biggest to the smallest. So we can say like for, range 2, we have the number 16 and 16 plus 8. That's this bit. And then inside of that, inside each of those, we could make them recursive calls, but so we can say we have 16 and we have 16 plus 8. And then we move on to the next bit, which is the 2's bit, or the 2 to the 1, the 1's bit. 1, 2, 3, yeah. So that's the 3's bit. And then we do the 2's bit, which is then we say it's 16 plus 2, and this plus 2. And then for each of those, but it's the 16 plus 2. Yeah. But 16 itself also has the plus 1 added to it. So it's like the first pass is plus 8 or not plus 8. Then these are plus 2 or not plus 2. And then it's like plus 1 or not plus 1. So it's like 16 and 16 plus 1. 16 plus 2 and 16 plus 2 plus 1. 16 plus 8 and 16 plus 8 plus 1. And then 16 plus 8 plus 2 plus 1. I mean, this feels like recursion, to be honest. And the positions that are being written to don't change. Or they do, rather. These are all the different memory addresses. Each time we kind of get one, it counts, which is something. Like we start out with all zeros, then we modify one thing, and we have 6, and we write to those the address each time. Yeah, I want to say that I could do this with recursion or just a for loop. And the fact that there are 8 combinations stems from the fact that there are 3 values being changed. Not that the value is the third bit, 2 to the 3 bit is active as a floater. So we could pre-calculate pretty easily. We would know up front that we would need 8. And we would know the kind of base case, 16. And each time we would add 8, right? And so you're like, do 16, write it off. Let's try this again. So we say 16, write it. 16 plus 8, write it. And then we would have 16 plus 8 plus 2. But the old 16 also needed the plus 2. So this is where I'm getting caught up. Keeping track of all the branching structures. Basically, it's a binary tree. Every call makes a split version. Splits. Right? So the first one is 16 and 16 plus 8. And that branches out to be 16 plus 2 and 16 plus 8 plus 2. So whatever came before it plus 2. Also, not like, what about the one where it doesn't add anything? That's not right. Because there's also 16 plus 8 plus 1 later. So it's like 16 plus 8 leads to 16 plus 8 plus nothing. And 16 plus 2. Like that, kind of. which still has 16 plus 2. And so now we have 16 and 16 plus 1. And then 16 plus 2 and 16 plus 2 plus 1. I guess that kind of works. As long as we get to the end and can recurse back up, okay. We need to, like, the weird part is the base case at the bottom of the tree is where we write to our registers. So yeah, because otherwise this is going to be tough to get all the combinations right. Right? So let's follow these instructions. Let's get this first part done first. Let's get our mask. We'll get our x positions and our kind of underlying number that we're going to apply the mask to. All right, here's our decoder code from before. We have a number. We only have an OR string. And so if it's x, OR string is 0. If it's not an x, mask is that. Then it just gets it. And that's it. It's really quite mundane. We could have just replaced all the x's with zeros and called it a day. However, we also want the count of the x positions. X position. Where are all of the x's in our thing? In reverse. Yeah, sort of. So I'm just going to do another pass because reasons. For v in num.reverse, string has no attribute reverse. What? Not what I expected. So if I have one of these masks, and I want to find the x, it tells me it's at 32, and I check from 33, 35. Oh, that's fair, it is at 35. And so until it's -1. And for each of these answers, like this one, I want it to be 0. So we need -35. All right, find while position not equal to -1, position equals none. So while we still have something to find, we're going to say the position is 0. And each time we're going to search for it, we're going to say num.find x. I have just changed my mind. We're going to use our friend enumerate, which we saw earlier, yesterday, a bunch. If v is x, at ith position, 35 minus I is one of the x positions. So x positions equals a list of numbers. Append. I'm not liking this. Okay, there we go. So we're going to return this and x positions. And we're going to call decoder at some point and get our OR mask and x positions. So for that given mask, we don't want this part. We still want the register, but we're not converting the number, we're converting the register. Interesting. All right. I'm going to go to the restroom. Man, this stream is taking a long time. Drank too much water. So I will be back in just a moment. Let's see here. Yeah. All right. So where were we? We need to find the location to put each of these memories, these memory addresses. So we're still, what do we write? Doesn't modify the value. All right. So we're going to modify the register that it's at, and we're going to the actual value, the num, we need the num. The number Alright, the number has been converted to an int, and we're going to call the decoder when there's a mask to create our mask for us. But we're not going to pass in the number, are we? No, we are. It's still the second half. But when the front is this, we're going to get the address, we're going to get the register, we're going to OR mask it to adjust it for the whole thingamajig. Though because of these X positions, just because it, it turns these into X's. And then in this example, it turns those numbers into, okay, yeah, these are decimal number 26. And we made the X's zeros. This is the part I'm concerned about, is that by making the X's zeros, it gives us a good starting point. But also, we probably shouldn't have converted all of the numbers. should I have an and string with all the zeros where the x's are so that they get zeroed out, so that we can have like a good place to start from, to add from? This ensures that we're always starting from 16, so to speak. Yeah, I think that's important. Okay, so we're still gonna have an and string, and that and string, whenever we come across an x, we'll have a 1. The or string will still have as or 0, and then when we come across something that's not an x, the and string will be whatever that value is still. Ooh. If it's a 1, we override it with a 1. If it's a 0, it is unchanged. So here, if it's a 0, what are we doing? If it's a 0, oh, now this should be an elif. Elif v is a 1? Oh, 0. Jeez, this bit stuff is wrecking me here. If it's a 0, so basically we're saying with the and string, all I want to do is turn the x's into zeros, right? We want to and the x's in such a way that it doesn't affect the other ones, but it changes the ones that are x's to zeros. So if I make them all 1s and make the x's zeros, all 1s, x's are zeros. So we add 1 regardless. Yeah, so instead of this, we can say in the and slot, and just always has a 0, 1, not a 1. Jeez. Oh. X's are zeros. Wow, I had this backwards. Okay. Oh, x's are zeros. The or string remains unchanged because the whole point is that the or, if it's a 1, the corresponding memory address is overwritten with a 1. So when the mask is a 1, we give it a 1 and it's good. If it's an x, we're going to have the or string be a 0, and the and will take care of that. They're both zeros. Yeah, so the and will take care of that. And then when it's a 1 or a 0, the and will always have a 1, which will leave it unchanged. Yeah, okay. This is not my best work. And mask. So the registrar gets kind of lowered down to the kind of base case. We need to be returning the and mask and picking it up. Int and string base 2. And then we have, let's see here. Try that. X is not defined. Indeed. What am I doing here? It's not X, it's 35. Our string is not defined. Typo here. From my Copy paste from before. Converted is not defined. Indeed, we don't know what to do just there yet. But eventually we want some kind of, but with combos. And put a comment there. So these are the positions. All right, so at most we have like, what is that? 1, 2, 3, 4, 1, 2, 3, 4, 9 to the 9th. Ooh. Not 2 to the 9th. Oh, yeah. 2 to the 9th. Combinations. Still, you know, counting to thousands is fine. 1, 2, 3, 4, 5. Yeah, 2 to the 9th is okay, I think. For a computer. Couple hundred things, you know, it's doable. It's probably not their favorite activity. Okay. You know, that's what makes this particular one rough, is because there's too many x's. So let's change our sample to consider the following program. All right, there it is. And we need to change this to that. And we have 18, the masks, 5 and 0. That's here, and 1, 2, 3, 4, 5. And so we're going to add the combinations of each one in a binary branching thingamajig. And then write it to those, write the number 100 to those locations. Okay? So we'll say something like, what do we need to have in hand then? For each one, we need to pass in the x positions. We need to pass in that base number, which is the register, the base register. Register. So we're getting this base number, a list of possible values, and the actual value to write, num. So write values. I don't think there's anything to return here. So let's, well, yeah, we also need to pass in that dictionary, mem itself. Memory, okay. So let's copy that and work on it up here. Def, write the memory. So we have the register. What is that one again? Oh, register value. So this is the base kind of, man, I need to make a comment here. Memory is this. Reg is base value starting register address value. X positions are 2 to the what? Shifts, and then, or not shifts, but additions, branching additions, really. And the number is the value to write to mem at address. Okay. Reg plus offset. Okay. And then so we can say if x position, the length of it is not 1, we're not done. So let's base case. If it is 1, we have one thing left in our list of powers. We'll start from the first one. All right, we're going to start from the first one. We'll say x position equals at 0. That's our power. So 2 to that power is the thing we're going to adjust for, right? That's our branch. And so we're going to call the next thing with, we're going to call right values. What just happened? Right values. Using a new starting base value, right? What is our starting base value? Oh, geez, down here. This is the last one. It's the base case. So we already have some register value coming in. And so we're going to say register plus whatever the shift is. And the other one is just normal register. There's no offset. And so we're going to say that memory at those positions are num. Memory at register of the X positions are num. Okay, we use all our things. That's always reassuring. Otherwise, right, we want to take one off, pass it around. 99 bottles of beer on the wall. Each time we want to take one off and call our branching structure with all the same sorts of stuff again, but like we have to modify it. That's always important in any recursive thing, and we have to call it twice. This is the part that I'm getting caught on. I'm not sure that my base case is right also. We start out with a bunch, and then we apply one of them, and that's our first branch. Those two calls each individually apply the next one. So when I call the next thing, I want to call it with kind of both left and right, so to speak. And I think the modification is to this base value. We also need to remove the remove one of the values from our list. So looking at this, I can feel the we're close. So it's like when we call it initially, we say we want 16 and plus nothing and plus 2 to the x. And then each of those says I'm going to call plus nothing and plus 2 to the x, or of the next thing, and take it off, right? So that's the modification scheme. So one of them just calls whatever called it and just passes it on, but with one less value. So in both cases, we're calling it with one less value, but in one of those cases, we're going to actually adjust it by this much. Right? Until we get to the end, and there's only one thing left. Hey, I think that works. Whoops. Okay. Apparently it did not work. So we call memory and we don't want to write to memory until the end. If length of x at position from 1 to the end, that should slice it down. Let's see why it's not. Oh, I didn't actually hit print. Good job, me. 0. Really? 2. 1. Well, why does it keep calling it? Boom. Return. That's embarrassing. Okay. So then I want to say, I want to print the memory register here. Actually, we have that somewhere. So make our recursive call. Then we see that we have, so with this first one, it's 26, 27, 58, 59. Ooh, this is nice. And then 16, 17, 18, 19. Oh man, that was crazy. Why is there 59 there? Oh, right, because that's how it goes. But where's 16? Oh, here's 16. Okay, okay. And the sum is 208. Oh, the sum is 208. How beautiful is that? Oh, nice. And we're printing this twice. Not loving that. Do we have to print it twice? We're in the for loop. We're printing it every time we come across a new line. Actually, what's interesting is that, oh no. All right, let's try it. Let's try it. Let's just let it print. Oh my goodness, it printed a lot. Maybe we shouldn't have let it print. Note to self, don't print so much. It's not gonna help our debugging, but it finished. Oh yeah. You know, that's what they say. The feeling of getting it after much frustration and head wrangling is so good. If I took away that print, does it? Oh my gosh, it just bam right there. It's done. Oh, all right. Nice. An hour and 8. These things are definitely starting to stack up in time. Yeah. So what? Let me know what you thought of that. Hope that was interesting. Watching me struggle through that little binary split recursion. Like, you know, the end result is really straightforward looking, but it's like trying to think through all the different cases here. Git add, git commit, AM, day 14. Whew, recursive memory register mods. Binary. What do we call this? Bitwise recursion prints. Right. Awesome. So thanks for, you know, tuning in, for those who could join today, and we'll see you tomorrow. Day 15, we are past halfway now. Very exciting, very exciting. And our little picture is coming together. You know, our Advent, you know, I don't know what it is. Our little, I still think it's either a ski slope or like a map of this island. Maybe it's like the route that we've taken, you know, to go from the various airports, and then this is like the island, and we had to get a ferry to the boat and something like that. But we are past halfway. I've got 28 out of 50 stars. Really cool. I just realized you couldn't see that. Here's the map I was just talking about. It is something. I don't know what it's going to be. Maybe it'll be like a little face or something. But yeah, we'll catch you tomorrow. All right, laters.